These are the practice problems that I distributed on Monday, March 6th, and they were due yesterday, March 8th. These were practice problems on acids and bases that were distributed on March 6th, and they were due March 8th for extra credit. And I'm going to go over them because this material is on the quiz on Thursday. There is a key posted as well. So number one, we're going to determine the pH of the following aqueous solutions. Hypoiodous acid. If we check our table here, it is on the Ka table, which means it has a weak acid with a Ka of 2.3 times 10 to the minus 11. If it's a weak acid, that means we need to write its acid dissociation reaction with a double arrow, where HIO dissociates into H plus and IO minus. Or you can write it with the HIO adds to water and then forms hydronium ion, H3O plus IO minus on the other side. Either way, you're going to have a Ka expression, which is going to be the products divided by the reactants. We're trying to calculate pH. If we're trying to calculate pH, that means we need to know the hydrogen ion concentration at equilibrium. So we're going to set up our Ka expression, and we know we need to figure out what is H plus at equilibrium. So for pH, we need H plus at equilibrium, so that means we need an ice table, everybody's favorite thing. So we're going to set up our ice table. 0.10 is the initial concentration. The other two initial concentrations are 0. I'm going to use minus X for the intact acid and plus X for both H plus and IO minus because it's a 1-to-1-to-1 stoichiometry. You get 0.10 minus X and X and X. I'm going to plug those into the equilibrium Ka expression. That's going to give us an algebraic expression, x squared divided by 0.10 minus x equals 2.3 times 10 to the minus 11. Next, we're going to make an assumption here. We're going to assume x is negligibly small compared to 0.10. We can certainly do that in this case because Ka is very, very small, 2.3 times 10 to the minus 11. So that's a 0.000, 10 zeros, and then a 2 and a 3. So that's a really small number, which means that this equilibrium is going to lie way to the left, which means that x, the amount that dissociates is x, that's going to be a very small number. Certainly going to be negligible compared to 0.10. But we will check it at the end to make sure that it's valid. So when we assume that x is small compared to 0.10, that reduces this denominator down here, the 0.10 minus x, reduces to 0.10. So that's going to change our expression to be x squared divided by 0.10. I'm going to cross part B out just to give us some more space. That means that x equals the square root of 0.1 times 2.3 times 10 to the minus 11. If you plug that into your calculator, you get 1.516575 times 10 to the minus 6. Now we can check our assumption, right? So we'll go up here and do that. So that means if we plug x in for 0.10, if we plug x in and we figure out what is 0.10 minus x, then you get the number 0.0999848. And this up here above this equal sign is a question mark. So this is questioning the validity of my mathematical assumption here. Between here and here, I made this assumption, 0.10 minus x equals 0.10. And now I see that that is indeed true because this 0.0999848 is what I get when I subtract x from 0.10. And then when I round that to 2 digits after the decimal, I still get 0.10. So that means my assumption was valid. I'm going to put a little check mark here above where the question mark was. And that means the last thing I need to do is I need to plug in x for the hydrogen ion concentration, right? Remember, x is H plus at equilibrium. So we plug that in, we solve for pH, and we get 5.81913. We need 2 digits after the decimal, 5.82. We're going to circle that as our answer. The reason it has 2 digits after the decimal is because both 0.10 and 2.3 times 10 to the minus 11 both have 2 sig figs. Now if we move on, I'm going to erase all this nonsense underneath part B so we can do part B. Part B is concentrated nitric acid. Nitric acid is a strong acid, and there are a lot of reasons you know that. There are 2 reasons that you know that. One reason is because it's on the list of strong acids. If we list out the strong acids, HCl, HBr, HI, those are the three hydrogen halides that are strong. HNO3 is nitric acid, HClO4 is perchloric acid, and H2SO4 is sulfuric acid. Nitric acid's right here on the list. Ta-da! It's one of the 6. Another reason you know it is because it's not on the Ka table. So this is our table of Kas. If you're not given a Ka for an acid, then you should probably think to yourself, I wonder if this is one of the 6 strong acids. Nitric acid indeed is one of the 6 strong acids. It's not on this table, so that means that that just further corroborates what we thought. So if it's a strong acid, that means it fully dissociates. And what that means is that we write it with a single arrow here. And that means that 15.8 molar nitric acid will go to 0, and that 0 molar products will each go to 15.8 molar. That means that we can plug 15.8 into our pH equals negative log of the hydrogen ion concentration to solve for the pH. pH equals negative log of 15.8, which gives me negative 1.198657. I'm going to round that to 3 digits after the decimal, because 15.8 has 3 sig figs. This is a negative value for the pH. You can have negative values. In class we talked about that. I think Cody mentioned that you can have negative pH values, which is true. You can also have pH values that go above 14. It just depends on whether or not it's a really concentrated sample, like 15.8, and also whether or not it's a strong acid or a strong base. Those are more likely to form more hydrogen ion. Part C is aniline. This is a weak base, and I know that because it is on the Kb table. I also know that because I saw that little NH2 there. The little NH2 in aniline makes it look like maybe it's an amine, which it is. It has a Kb of 7.4 times 10 to the minus 10. I'm going to write the base dissociation reaction where we add water on the left, and then water transfers its hydrogen ion to aniline to form anilinium ion, which is this C6H5NH3 plus hydroxide. We write the Kb expression. And we need to solve for the pH. So if we need to solve for the pH, that means we need to know the hydrogen ion concentration, which we do not know, but we can relate it to the hydroxide ion concentration here, which is part of our reaction equilibrium, right? So if we can figure out hydroxide ion concentration equilibrium, we can from that calculate the hydrogen ion concentration, and then from that get the pH. So that means we need another ice table. Yay, ice tables, they're so fun. So we'll set that up. 0.95 molar is the initial concentration of our base, and then the others are all 0 molar. Water I x'd out because we don't care about that. Minus x's and plus x's, minus x on the left, plus x on the right. And then at equilibrium we have 0.95 minus x, and then x and x. Now we're going to plug those things into our Kb expression and set up our algebra. We get x squared divided by 0.95 minus x equals 7.4 times 10 to the minus 10. We're going to assume x is negligibly small compared to 0.95, just like we did for part A. That's a reasonable assumption since Kb is 7.4 times 10 to the minus 10. That's a very small number. We're going to plug it in, and then we're going to solve for x. That means, so our assumption here reduces this denominator to 0.95. Here I skipped a step that I did before. Instead, so this would be x squared divided by 0.95 equals 7.4 times 10 to the minus 10. And here I've already solved for x. X equals the square root of 0.95 times 7.4 times 10 to the minus 10. And that's going to give me 2.65 times 10 to the minus, it looks like, what is that number? I can't read the number I wrote. My pen is too fat for this iPad. That is a 2.65 times 10 to the minus 5. That's a minus 5. And then if we plug that in, I'm going to check our assumption. 0.95 minus x, the question mark is that really the same thing as 0.95? So if we subtract the x value we got, 2.65 times 10 to the minus 5, then you end up getting 0.949973, which certainly rounds to 0.95 when we round it to 2 digits after the decimal. So the assumption is valid. I'm going to check that. And I'm going to plug x in. Now remember, x is equal to the hydroxide ion concentration. So that means we're not solving for pH. We're solving first for POH. I'm just going to cross this out so we don't get confused, and it saves us a little bit of space. So X is hydroxide, that means the POH is the negative log of X, negative log of 2.65 times 10 to the minus 5, and that gives me a POH of 4.576, and then the pH is 14 minus that number, which is 9.423477. We have 2 digits after the decimal. That's because the numbers we're given are 0.95, and 7.4 times 10 to the minus 10 is KB. And so in our math up here where we did the square root, the product here has 2 sig figs times 2 sig figs, which is going to give us 2 sig figs. The square root will still be 2 sig figs. So our X value is accurate to this 6, 2.6 times 10 to the minus 5, which means we have 2 digits after the decimal point, and that is our pH. Now, this is also, remember, it's a weak base, and so the pH I get is greater than 7. Part A was, this accidentally says Part A, it should be Part C. It renumbered them when I made these slides. So anyway, this is a weak base. We should get a pH greater than 7. Part A was a weak acid. Part B was a strong acid. For both of those, you should get a pH below 7. So you should verify that as you're going. Now, number 2, I'm going to have to erase all this extra stuff. Here we're putting things in order from highest pH to lowest pH. Now, we need to classify each of these things. We did this one in class, actually, so if we're going to we need to look at each one and decide what it is. Potassium hydroxide is a strong base. It's a metal hydroxide. Propionic acid is a weak acid. I know that because it's on the Ka table and because it's not on our list of strong acids. It's not on the list. So we're going to, then we can also look at the Ka table, and it is here. Propionic acid has a Ka of 1.3 times 10 to the minus 5. So I'm going to write that down, 1.3 times 10 to the minus 5. Now, acetic acid is also a weak acid. It's also not on the list of strong acids, and it's also on the Ka table. Acetic acid is at the very top, 1.8 times 10 to the minus 5. I'm going to write that down too, right here, 1.8 times 10 to the minus 5. Chloric acid is kind of a medium acid. Chloric acid is the one that we debated, should it be on the list of strong acids? Sometimes it is and sometimes it's not. It's not on the list that we have that your book uses, which is fine. It is on the Ka table, right? It's not on the list. It has a Ka of 1. Chloric acid is right here. So it's pretty strong for a weak acid, but it's a large Ka for sure. So we're going to write Ka equals 1. Ammonia is a weak base. It has a Kb on the Kb table. At the very top, 1.8 times 10 to the minus 5. It goes right here. Magnesium hydroxide is a strong base, and it forms 2 hydroxides per magnesium hydroxide. So magnesium hydroxide is going to be the most basic because it's a strong base, and it also forms double the hydroxide ion concentration as the potassium hydroxide does, which means that out of these 6 compounds, the strongest base is going to have the highest pH. So I'm going to list that last. It's number 6. Potassium hydroxide, the first one listed here, is going to be number 5 because it's also a strong base. The only other base on the list is ammonia, and therefore, being the weakest base, it's going to be number 4. Now these 3 remaining ones are all acids. The strongest acid is chloric acid, so it's going to have the lowest pH, so it's going to be number 1. Of these 2 remaining ones, acetic acid has a higher value for the Ka, which means it is a slightly stronger acid than propionic acid, so it's number 2 on the list, and that one's number 3 on the list. Now water, if we had it on our list here, would be in the middle. It would be right in the middle of this. It would be between ammonia, which is the weakest base, and propionic acid, which is the weakest acid. Number 3, we have a 0.10 molar solution of acetic acid with a pH of 2.87. We're going to calculate Ka, which means we need to write the acid dissociation reaction here, where acetic acid loses its hydrogen ion, and then we'll write the corresponding Ka expression here. And so all we need to do is figure out what these values are at equilibrium, and plug them in, and we'll be done. So if we want to determine these, that means we need an ice table. Everyone's favorite thing. So we'll put that over here. We know the initial concentration of acetic acid is 0.10. We know the initial concentration of our products is 0. Now, the only other thing we know is the pH is 2.87. So if we know the pH is 2.87, that means we know the hydrogen ion concentration equilibrium must be 10 to the negative 2.87, which is 1.34 times 10 to the minus 3 molar. We'll plug that into our ICE table right here. That means that the change in H plus must have been plus 1.34896 times 10 to the minus 3 molar. And that means that the plus x and the minus x on each side must also be the same value. And that means that at equilibrium, the acetate concentration, our conjugate base, must be 1.34896 times 10 to the minus 3 molar, just like hydrogen ion. And then our equilibrium concentration of the intact acid must be 0.10 minus that number, which is 0.098651. We plug those three numbers in to our K expression. We plug them in there, and we get this number here, 1.34896 times 10 to the minus 3 squared divided by 0.098651, which gives us 1.8 times 10 to the minus 5. Number 4 is the last question. We're going to put these acids in order from strongest to weakest. So strength of the acid is determined by how much it dissociates. Strong acids completely dissociate, and weak acids do not dissociate as much. So here we're going to count how many intact HX acids are left. There are 2, and then there are 1, 2, 3, 4 X minuses. 1, 2, 3, 4. So 4 X minuses. Now if we look at HY, there are 1, 2, 3, 4, 5 intact acids and just 1 dissociated conjugate base. If we look at HZ, there is no intact HZ left. It's only Z minus. 1, 2, 3, 4, 5, 6 of those, 6 Z minuses. This is fully dissociated, which means that it is a strong acid, which means HZ is the strongest. HY is the weakest, and I know that because it dissociates the least, and therefore it is the weakest, right? So there's more intact HY molecules than there are of the others, and therefore we're going to put them in order from strongest to weakest would be HZ, then HX, and then HY.